Hey there, we're back here in the Laurel Forum, Carpent Hall 139. I've got one more section to deal with from chapter 9, and that is section 9.5. So far we've learned about a number of different combinatorial or counting techniques, including the addition rule, difference rule, multiplication rule, which was related to possibility and probability trees. We looked at the pigeonhole principle, we looked at permutations, the number of ways of counting a way of counting the ways that objects from a set can be collected. Related to permutations, we're going to look at the idea of a combination today in section 9.5. This, as I said, this will be related to permutations with a slight difference, and we'll talk about that in a moment. Before I get into it, though, I just want to remind you all, make sure you're staying up with the work. If you haven't already done so, turn in your problem sets from the remaining sections of chapter 5, which were due a couple weeks ago, but I'll take them late if you haven't gotten them in yet. From the first few sections in chapter 9 were optional because I want you to be focusing on the second exam, which is due this evening as I record this. No, I'm sorry, tomorrow evening as I record this, Friday. So I'm recording this on Thursday the 16th. Friday the 17th is when that exam is due. I'll get that back to you as quickly as I can over the weekend or early next week, and you'll have a chance to do some revisions and get that in for partial credit back if you need to. So again, stay on top of things, get in touch with me if you need to. We've got office hours still, Monday and Wednesday mornings from 9 to 10. I'm available. Check in with Stephen Robinson, check in with the Math Lab. They've done a wonderful job of staying accessible in this era. So if you need help, reach out. I'm there. I'm happy to meet with you at a time convenient for you. So back to chapter 9.5, or section 9.5. We're going to look at combinations. This is really the last idea from this chapter that I wanted to talk about before we move on to a few of the sessions from chapter 10 to round out the semester. So the idea in this section is the idea of an R combination. And the R here just refers to the size of a set. We're going to look at, throughout all of this, we're going to look at a set of n elements. Just take a bag with your favorite n objects in it, and there's our bag. In here we've got our favorite objects. I don't know, a pair of scissors, your mother's lucky needle. Let's see what else is in there. A little matchbox car of some kind that you played with in childhood. And you got your laptop in there. That's a really indispensable element these days. We got a book. There are a bunch of objects in this bag. And what we're going to do, kind of like when we looked at permutations, we're going to select objects from this bag. The difference being, in a permutation, you had, let me get to combination first, and then we'll talk about the difference. In a combination, what we're going to do is we're just going to reach in and select from this bag a collection of R objects. So from a set of n objects, select R objects. And this selection is called an R combination. An R combination, if you want to be precise, of the original set. So that's all an R combination is. It's a collection of, or a subset of, R objects chosen from among n. And the question we have is, how do we count the number of such combinations? It's related to permutations, but it differs in a very specific way. Notice, if we're selecting R objects from a set of n objects to form a subset of size R, it's a subset. It's a set. It's not a list in which order matters, like picking the first one, then picking the second one, then picking the third one, and so forth, kind of like we did when we looked at permutations. In this case, it's a set where order doesn't matter. In fact, that's going to help us count the number of ways this can be done. Because if we're selecting R objects from among the n objects, it doesn't matter the order in which we pick them. In other words, every permutation corresponds to a combination if we just forget about the order. So notice that an R permutation, and that is an ordered selection. So just to emphasize, this is an ordered selection of R objects. Corresponds to an R combination just by forgetting about the order. Corresponds to an R combination by forgetting order. Once you have a list of your objects and you just forget about the order they appear in, so you're just looking at the set instead of the list, you get an R combination. In fact, we can go the other way too. We just have to recognize that now giving an R combination, there are lots of different permutations, right? So on the other hand, if we start with an R combination, we get many different R permutations corresponding to it. How many? Well, we can figure out. I'll leave a blank there. We'll figure it out in a second. We get blank different R permutations. Well, let's see if we can figure that out. Here's an example. I'll just kind of play around up here. This is our play zone. Let's say, for instance, I've got 5 objects. So inside of a larger collection of n objects, I've picked R equals 5 objects. I've got 1, 2, I'm going to make them slightly different shape from each other. So I've got 5 different objects in there. Now, if I want to count the number of ways, this is a 5 combination from inside this larger set of n. And if I want to count the number of permutations it corresponds to, I want to count the number of ways of listing those 5 objects. So I take those 5 objects, that's just one combination, right? No matter what order I put those objects in, it's just one combination. However, if I start to think about putting an order on them, I can put the dot first, and then the diamond, and then the box, and so forth. Or I could permute the order a little bit. I could put the circle before the diamond, box, star. There are clearly lots of different ways to do this. To count them, however, we just go back to the multiplication rule. So I want to ask myself, how many ways are there of picking the first guy? Times how many ways are there of picking the second guy, and so forth. So using the multiplication rule, we have 5 ways of picking the first element. Once we've selected that element, we multiply by 4 for the number of ways of picking the second element. Now we fix the first 2, and we have 3 elements remaining for the third position. For the fourth position, and by the time we get to the end, we're stuck. We have just one choice to make. There's only one object remaining. So in this case, when we had R equals 5, there were 5 times 4 times 3 times 2 times, that's our familiar, by now hopefully familiar 5 factorial. That's how many ways there are of taking a single R combination and making an R permutation out of it, where order matters. In other words, every 5 combination gives rise to 5 factorial. It's a pretty big number already. 5 factorial are 120 different 5 permutations. Going back down to our general case, if we start with an R combination, we get, well, extrapolating from this reasoning here, R factorial different R permutations. Now this is really important because, go ahead and turn the whiteboard around. This is really important because it gives us a way of computing how many R combinations there are in a given set. Since the number of R permutations, remember this is ordered lists, the number of ordered lists of size R in a set, or I guess of a set, of n elements is, and we talked about this formula the other day, it is n factorial divided by n minus r factorial. We came up with that formula, in fact, by much the same reasoning as on the other side of the board. We just looked at the number of ways you could assign n different, pick r different elements from among the n in some ordered fashion. Since this is the number of r permutations of a set of n elements, the number of r combinations is going to be smaller, because remember, many different r combinations correspond to a single r permutation. In fact, we know how that correspondence goes. We just saw that we had r factorial combinations for every permutations. The number of r combinations of a set of n elements is, again, we have fewer of them because now order doesn't matter anymore. And for every one of these, what do I want to say? Yes, every one of these collapses. There are r factorial of these that collapse into a single r combination. And that means that we have r factorial times fewer of them than we had permutations. How do we get that? We start with our formula. We start with our formula for the number of permutations, and we multiply by 1 over r factorial, because that's the rate at which, or the factor by which the number of combinations diminishes from the number of permutations. That is a formula that should look kind of familiar when we put these two fractions together. Multiplying fractions, we could just put the denominators together. Look at that. That look familiar? Pause the video if you need a second to think about it. Go ahead and pause the video. And unpause when you're ready. This should look like a binomial coefficient. N choose R. That's it. So it's another way that binomial coefficients come up in our work. Binomial coefficients help us count the number of R combinations in a set of size n. If you want to choose R elements from a set of size n and you don't care what the order is, you just use the binomial coefficient formula and choose R. Cool. So let's look at some examples here. Let's suppose, let's do a collection of related examples, give you a quick quiz, and we'll be on our way. On our merry way. Let's suppose that we have a committee that is to be chosen. The homework selection committee is to be formed from 6 students in our class. So we must select 6 students from 21. Remember, that's how many folks are in our class, are registered right now, to make a committee. So I've got 3 related questions for you, and we'll answer them in turn. 1, if there are no other restrictions, all we need is 6 people, we don't care which ones, no other restrictions on committee membership. How many committees are possible? That's the simplest question we can ask, like, no other restrictions, how many committees are we going to have? If 3 students must have last names starting with A through M, and 3 with last names N through Z, same question. How many? How many committees are there where 3 members come from the first half of the alphabet and 3 come from the last? And then finally, what if we only need at least 1 from each half of the alphabet, A through M and N through Z? See, the second 2 problems, the first problem is just straight up combinations. How many combinations of a certain size are there? Second one is going to involve a little bit of multiplication rule. And then the third one is going to entail the multiplication rule and the addition rule, working in conjunction with one another. So let's see how this goes. After a brief pause, to erase. I could be editing this out, but I know this is time for you to go to the bathroom, grab another soda, etc. Or take a quick run around the block or something like that. All right. So we've got 21 students in our class, and we want to pick a committee of 6 of them. So the first question is just no restrictions. And in that case, all we have to do is ask ourselves, well, how many ways can I pick 6 objects from among 21? This can be done in 21 choose 6 ways. That's all. Very simple. Of course, just to get a little practice with this, 21 choose 6 is what? 21 factorial divided by 21 minus 6 factorial times 6 factorial. That's all the numbers 21 down to 1 multiplied together. 21 minus 6 is 15, so we get all of those numbers multiplied together. And then finally we get 6 times 5 times 4 times 3 times 2. Now, we get a lot of cancellation, right? Because of this factorial being present, that cancels out most of the top guy. And we only have the very first terms up to 16. Of course, that cancels out the first factorial here. But now we can notice, well, 5 times 4 is 20. Cool. 6 times 3 is 18. Awesome. 2 goes into 16 and leaves 8. So really all I've got left is 21 times 19 times 17 times 8, which is a number that I should have considered ahead of time, and I did not. One moment, please. 21 54,264. So if there are no restrictions on the structure of the committees, we can do it in a little over 54,000 different ways. However, the second question asks us to choose 3 from the A through M portion of our class, and 3 from the N through Z portion of our class. Now I happen to have looked this up ahead of time. This I did do, so I'm not entirely lazy. It turns out there are 13 people from A to M in our class, and there are 8 people from N to Z. So, this can be done. I mentioned that we're going to do a little bit of multiplication rule here. The trick is to notice that we can pick our first 3 totally independently from our second group of 3. That means we can select our subcommittee of 3 people from 13, and then our subcommittee of 3 people from 8. And all we have to do, since they're done totally independently of each other, and for every one of these subcommittees, we can mix and match it with any one of these subcommittees. Multiplication rule says just multiply them. That's it. And let's see, just for fun, how this works out. 13 factorial divided by 8 factorial times 3 factorial times 8 factorial times 5 factorial times 3 factorial, right? No, that's not right. That should be a 5, right? Because that should be 13 minus, 13. What am I even doing? I have no idea. No, this one's right. This one, however, should be 10 factorial times 3 factorial. Don't even listen to me. That's the moral of the story. This is why you shouldn't skip steps, by the way. I skipped this step right here and messed up the basic arithmetic. Now it's right, I think. All right, so let's just see. 13 factorial cancels with the 10 factorial mostly. We just get the 13, the 12, and the 11 remaining divided by 3 times 2. Over here, the 8 factorial and the 5 factorial cancel out a lot. We get 8 times, totally forgot about 7, times 6, divided by 3 times 2, right? And we canceled out much of those with this fact, etc. Okay, and now we've got what? 13 times 11, but now 6 goes into 12 and leaves 2, times 6 just gets canceled and we get this product. Let's see what this is. All we know is that it's going to be smaller than what? Make sure that you pause the video and convince yourself that it's got to be smaller than this number right here, because this is no restrictions. This is with some restrictions added. So all we know for sure is that this number down here is going to be smaller, and in fact it is. This turns out to be 16,016. So a little over 16,000 possibilities. Way smaller than 54,000 because there are further restrictions we placed on this kind of committee. Now, the last example, go ahead and pause the video before I work this out to see if you can figure out how to do this. Remember what it was is the only restriction, it's a little looser than this restriction here. The only restriction now is that at least one person has to be chosen from either half of the alphabet. So choose at least one. From A to M and from N to Z. Let me make sure that we are clearly separating these now. So it's a little looser restriction, as I said. Pause the video if you haven't already and figure out how we're going to do this. It's the same idea as number 2, only now we're throwing the addition principle in as well. Additionally, you might say. All right, so this was the way of choosing 3 on either side. But now we can choose well, we need at least 1 from the first half. So we can choose 1, the number of ways of choosing 1 from among the 13, times the number of ways of choosing the remainder from the second half. But since there are 5 left over, right, we want a committee of 6. We've chosen 1 from the first half, so it must be 5 from the second half. This is the number of ways of choosing a committee where 1 comes from the first half and 5 come from the second half. To that, we must add the number of ways of choosing 2 from the first half and 4 from the second half, plus the number of ways of choosing 3 from the first half and 3 from the second half. That's this case here. Plus the number of ways of choosing 4 from the first half and 2 from the second half. And finally, the number of ways of choosing all but 1, 5 from the first half and 1, that remaining person, from the second half. I am not going to go ahead and add this up. I'm going to let you do that to get some practice with binomial coefficients. All you know, of course, is that this middle term is 16,000 and some. Clearly, this term is going to be bigger than 16,000 because it has this term in the middle, and that makes sense. This is a looser restriction. The restriction we had in the second case is kind of embedded in this one. So it's clear we're going to have a broader array of committees here, and therefore more possibilities. But it's also clear it's going to be less than this because this was no restrictions whatsoever. So go ahead and work that computation out and verify that it's between these two values. Just to get some practice with binomial coefficients and factorials. And for your quiz, I think we're nearing the end here. Let me give you one more quiz. And this is going to be due on April the 24th, I believe. So quiz CE9, COVID era 9. Just some more practice with binomial coefficients. If n equals 5, find the number of R combinations for each of R equals 0, 1, 2, 3, 4, 5. So with a set, given a set of 5 elements, tell me how many ways there are of creating 0, a subset of size 0, subset of size 1, subset of size 2, and so forth. Don't forget, we talked about this, I think we talked about this even before we broke for spring break and therefore COVID. I think we talked about the fact that 0 factorial, when 0 gets really excited, it becomes 1. So 0 factorial is 1, and that'll help you with these computations here. I believe that quiz is due on Friday the 24th. Just upload directly or type directly inline your response to the quiz in Moodle, and I'll see it there. And I will see you. Please do check in with my office hours, again, Monday and Wednesday from 9 to 10. If those times don't work for you, I'm happy to make an appointment. Otherwise, shoot me an email. I'll help you by email. Math Lab's open, etc., and work together on this stuff. I hope y'all are collaborating behind the scenes. I'd really like to see you develop that community of folks who are working on these problems together. Well, thank you so much, and I'll talk to you soon.